So we're going to start this video talking about something called dimensional analysis, which in reality is just a fancy way of saying unit conversions. However, there are some things about dimensional analysis that make it a little different than your typical unit conversions that you've seen in previous science classes. So in previous classes, you get a problem that would say something like, if you use 7,200, 0.4 centimeters, how many millimeters is this? And there's a couple ways you can solve it, but the most common way you probably solved it was to use something called the metric stairs. So this is a copy of the metric stairs. I'm sure you've seen it before. The basic idea is something like this. Your base unit starts right here on this middle stair, and that would be your things that don't have prefixes. So meter, gram, liter, these are your base units without prefixes. As you go up the stair, so as you go this direction, the units actually get bigger. So deca is 10 whatever your base unit is, hecto is 100 of whatever your base unit is, and kilo is 1,000. You probably know this because you've seen kilograms be 1,000 grams or kilometers be 1,000 meters. As you go the other way, which is this direction, the units get smaller. So deci is 1/10 of your base unit, so 1/10 of a millimeter, 1/10 of a meter, sorry, 1/10 of a gram. Centi is 100th, and milli is 1,000th. And the way the metric stairs work is you actually figure out where you're starting and where you're finishing, and that tells you how many ways and in which direction with the decimal. So in this case, we have 7,200.4 centimeters. So we're actually on this stair. So that's 7,200.4. Here's my decimal. And we're going from centimeters, and we want to go to millimeters. So this is one step. It's this stair right here. So we're going to go one step down to the right. And as we do this, since we went one step to the right, we're actually going to move our decimal one to the right. And that means that 7,200.4 centimeters is equal to 72,004 millimeters. And this is the way you've done it for a long time, and it works perfectly fine when converting quantities of the same unit. Unfortunately, this isn't the way that we're going to do unit conversion in this class anymore. The reason being is, one, this is a much more grown-up and kind of professional way to solve problems. And two, you're often converting between units in chemistry. So if we can use the same process for converting all different things, we're going to use one process to make our lives simpler. And that process, once again, is called dimensional analysis. In dimensional analysis, you're expected to once again still know how far above and below things are of the base unit. So for example, you should know that a kilogram is 1,000 of the base unit, or that a centimeter is 1/100th of a meter. One thing I will tell you is if it's something unusual in this class, I will give you the conversion. So I'm not expecting you to know things like giga or mega or pico, but the common ones, centi, milli, and kilo, you should have a very good handle on those three. So the way dimensional analysis works is dimensional analysis actually uses something called the identity property of multiplication. It's this idea that any number times 1 is equal to the same number. You were actually able to convert units doing this, and I'll show you an example in a second. But right now, you should be familiar with the idea that 4 times 1 is still equal to 4. I can also write 1 as a fraction as long as my fraction is equivalent. So I could say 4 times 7/7. That's also equal to 4, and the reason being is 7/7 and 1, these guys are both the same thing. So these are the same right there. So how does this work in dimensional analysis? Well, let's think about those equivalent fractions to 1. Remember I wrote 7/7 is equal to 1? Well, the same thing if I wrote 1 meter over 1 meter, that fraction is also equal to 1. But there are other fractions that are also equivalent that don't have the same units on the top and bottom. For example, if I wrote 100 centimeters over 1 meter, this fraction is still equal to 1. 100 centimeters are there are 100 centimeters in 1 meter, and even though these units are different, the multiplying by this fraction doesn't change how much of a quantity that you have. So for example, if I had 1 meter and I multiplied this, I could turn it into 100 centimeters, but I still have the same amount of length. Also, the other thing that you should notice is if I turn this fraction upside down, so if I put 1 meter on top and 100 centimeters on the bottom, the fraction is still equivalent. All of these fractions are equal, and they all equal 1, and this is how dimensional analysis works. So with dimensional analysis, you often get a problem like this one, which says something like, how many kilometers are in 452.0 meters? And the way we work dimensional analysis, we actually do what we call our starting values. This is where we're going to start. And we're given this value in the problem. For example, this one is 452.0 meters. The second phase is actually our conversion factor. So we're going to multiply our starting value, which is 452.0 meters, by a conversion factor. And the way it works is pretty simple. We write the multiplication sign, and then we draw a division sign. It is really important that you do these steps first. So then we're going to ask ourselves the question, what unit are we trying to get rid of? So in this problem, we actually start with the unit of meters, which is right there in the problem. It's also right here. So we want to get rid of meters. So the one we're getting rid of, we put that on the bottom. So I'll make a note here that on the bottom, this is the one you're getting rid of. And then we ask ourselves, what is the unit that we're trying to change to? So this problem asks for your answers in kilometers. So we're trying to change to kilometers. So that goes on the top of the fraction. So this is the change to. And I'll put that in green so you know it. And when you solve these problems, it is extremely important to put the units first. I know a lot of you don't like showing your work, but you're going to make mistakes if you don't put the unit before you write the numbers. So in this case, I put meters on the bottom because I'm trying to get rid of it, kilometers on top. Then I ask myself, what's the conversion factor? So this, unfortunately, is one of the ones you have to have memorized, but you should know that in every 1 kilometer, there are 1,000 meters. And you can look these up if you need them, but really for kilo, centi, and milli, you should have them memorized. This is 1,000 meters for every 1 kilometer. Finally, the last step in the problem is we just solve it. And it's a basic multiplication problem. This actually is over 1, but we don't write that because that's not appropriate. So what we do is we multiply 452.0 times 1, so the multiplication right here, and then we divide by 1,000. And when you divide by 1,000, it actually ends up being 452.0 divided by 1,000. And then it gives us an answer of 0.4520 kilometers. Notice that I kept the 0 here. The reason I kept the 0 here is because in conversion factors, there are infinite sig fig. Conversion factors are actually counted. So there's infinite sig fig here. So the lowest sig fig comes from our starting value right here, which had 4 sig fig. Therefore, we need 4 sig fig in our answer, which is why I kept it at 0.4520 kilometers. So notice here's another example problem. How many liters are in 6.71 hectoliters if there are 100 hectoliters in 1 liter? And notice this is the unusual conversion factor. I don't expect you to know hectoliters, so I gave it to you in the problem. So once again, let's get our starting values to set it up. Our starting value is 6.71 hectoliters. Our conversion factor, now remember, we're multiplication sign, we draw our division sign, and this time we're trying to get rid of hectoliters, so we put hectoliters on the bottom. We're trying to turn it into liters, so we put liters on top, and we know that there are 100 hectoliters in 1 liter, which gives us to an answer of 6.71 times 1. Multiply that, divide it by 100, and you get 671 liters. And once again, 3 sig fig here, 3 sig fig here. So we're in good shape. And these are the kind of problems you're going to see. So this is yet another problem, but a little bit different. And this time we're not converting between the same base unit. We have completely different units. However, we can still use the same process to solve the problem. So this one says an astronaut has a mass of 187 pounds. If there are 2.2 pounds in every kilogram, what's the mass of the astronaut in kilograms? So it's pretty simple. We're starting with the astronaut who has a mass of 187 pounds. So we're going to write that there. Then we put in our conversion factor. Remember, draw the multiplication sign, draw the line. We're trying to get rid of pounds, so we put that on the bottom. Of course, we're running our units first. Then we're trying to turn it into kilograms. Kilograms goes on top. And we know, numbers-wise, that for every 1 kilogram, I have 2.2 pounds. And then I can solve it. 187 times 1 is 187. When I divide it by 2.2, I get 85.0 kilograms. And once again, 3 sig fig here, 3 sig fig here. This has infinite sig fig. This has infinite sig fig because it's a conversion factor. And I know there are 85.0 kilograms in 187 pounds. So this last problem is a great example of why we use dimensional analysis. This problem says the distance of a marathon is 26.2 miles. If 1 kilometer is equal to 0.621 miles, how many meters long is a marathon? Well, we're starting with something obvious. We're starting with 26.2 miles. So we're going to put that first. However, the conversion factor we're given, so this is the first conversion factor, and we'll draw the line, is miles to kilometers. So we're going to get rid of miles and change it to kilometers, so kilometers goes on top. And we're told that 1 kilometer is equal to 0.621 miles. The problem is now my answer is in kilometers. It's not in meters. That's the question's asking for meters right here. So I actually can multiply it by a second conversion factor. In this case, I'm getting rid of kilometers, which I'm in, because remember now they've changed to kilometers. I got to get rid of it. I want to put it into meters, and you should know that there's 1,000 meters in every 1 kilometer. And then we're ready for an answer. So when I solve it, I can solve it in one step. It's 26.2 times 1 times 1,000. Divide that all by 0.621. And when I come up with an answer, I get 42,100 meters. This is perfectly acceptable because this has 3 sig fig right here, and so does this. But if you want to be really fancy about it, you could always call it 4.21 times 10 to the 4, just to get our scientific notation back in there. For some of you, this is the first time you've seen doing conversions this way, and that's okay. We're going to do a lot of this in this class, and this is a skill you have to have and have to be able to do correctly. So what are the keys to success? I think the very first and probably most important key to success is show your work. A lot of you can do these unit conversion problems really quickly and do them in your head, even doing the metric stairs in your head. I know that's how I do it. But if you show your work, it shows me that you understand and you're going to make fewer mistakes. The second key, and this is also really, really important, the second key is write the units first. So when you're writing a conversion factor, write your units first and make sure that the unit you're in and trying to get rid of is on the bottom and the unit that you're trying to change to is on top. Do this before you write any numbers in that fraction. And then finally, the third step is check your work. I can't tell you how many times you guys just solve a problem and don't have any number sense about it. So for example, if I said to you a marathon is 26.2 miles, how many kilometers is that? And you give me an answer that's like 100 million kilometers, or you give me an answer that's like 0.5 kilometers. Neither of those really make sense in the context of things. So look and see if your answer makes scientific sense before you give it. There are 2 practice problem sets that allow you to do this, and there's also the written notes on Schoology, which are after this. So both of these give you an opportunity to review this if you get stuck, and you can always rewatch the video. I'll be back on Thursday, but until then, good luck.